with the problems I chose. You invent the problem. Give me any linear function you can think of.
X plus 30.
Thank you. And you want that to happen when x approaches? 2. Very good. And the limit is, because it's polynomial, we have a theorem from last time, and the limit is?
2.
Very good. We know this. So now we want to show what's behind the curtains, okay? Why this happens. So now we use this symbol, which is a double equivalency. What does this mean? This implies what I'm going to write on the other side. What I'm going to write on the other side implies this. It's a double equivalency. And now let's use those symbols. So I can explain the symbols now. This upside down A stands for every. For every. For any. For each. Epsilon positive, as we discussed. The next symbol is this. These are all not inventions. These are all mathematical symbols. And if as higher you go in math, you will use potentially these symbols. So it's not. I'm not going to test you on this. You can write in words if you don't like to use the symbols. So for every epsilon greater than 0, there exists, or I will find, there exists. Or if you want, I will find. For every epsilon greater than 0, I will find. There exists. What? What will I find for every epsilon? A corresponding? Very good. Which has to be greater than 0. So for every epsilon greater than 0, I will find, or there exists, a delta greater than 0. Such that, so this is a uppercase. Such that, this is a smaller e backwards. For every epsilon greater than 0, there exists a delta greater than 0. Such that, this is a, it's like a, what is it, the euro sign. Similar. Okay, so for every epsilon greater than 0, there exists a delta greater than 0 such that. And now this is the key. When I pick x close to 2, how do I write when I pick x close to 2? Here's how I write it. 0, x minus 2, less than delta. So this means, and you can say, why do you use this? Everybody knows that the absolute value is greater than 0. Why would you put this in here? Exactly. Thank you. That's why I want, because otherwise I could pick x to be 2, and I'm not allowed to, as we know. Excellent. Thank you. So let me write this, what this means. So such that every time I pick x close to 2, in other words, the distance is not more than delta, what will happen? This implies, what will happen? So I know that for every epsilon greater than 0, there exists a delta positive. I will find a delta positive such that what? Every time I pick x close to 2, and I should write in parentheses for this, not 2, this implies, or what will happen when I pick x close to 2? Exactly. And this is how we will write it. The distance between f of x, for this x, that's f of x, will fall within epsilon of 11. It looks gibberish, right? It looks difficult. You'll see it's just a straightforward proof. For every epsilon I pick, and I don't want to pick one, I just want to show the relationship, so it's just epsilon in general. I will find a particular delta that depends on epsilon. Delta has to have epsilon in it, because as you saw, for every epsilon, I had to divide by 3 to get the delta. So epsilon is given. For every epsilon that is given, I will find a corresponding delta, a different one all the time, because epsilon is different, such that every time I pick x close to 2, not further away than delta. The distance between x and 2 is not more than delta. So I pick x close enough to 2. That will result in f of x, f of this particular x that I pick, the distance between f of x and the limit, which is 11, has to be within epsilon of 11. So the distance between f of x and 11 has to be smaller than epsilon. Okay, so now I wrote this. How do I show all this? Here's how I do it. I start from the end. Can anyone dictate what I should put in here? Well, I have to replace f of x by, what is f of x in our case? You pick the problem. Yes. So this gets replaced by 4x plus 3. Then please continue for me. Yes, less than epsilon. Less than epsilon. Good. Now here's my target. I want to find delta. This is my target. I want to get here. Okay, so please tell me what to do next. If you're given this, what will your mind go to? No. Just look at it. Just look at it. What will you do? Yeah. What? Yes. What will you do? Perfect. What will you do next? Simplify factor, simplify factor, simplify factor. Good. Now I have to refresh your memory. Don't forget what you want to say. Forgive me for interrupting. I need to refresh your memory on this. The product, the absolute value of a product, what does that equal to? The absolute value of A times the absolute value of B. And I have to write this. I cannot jump. I cannot factor out of the absolute value. I have to use this property. So what would be the next step? Yes, please.
Shouldn't that be 4x minus 8?
4 times x is 4x. 4 times 2 is 8. Factor.
But you said mom like terms.
Oh, minus. I'm sorry. Thank you. Oh, yeah, of course. Of course. I'm sorry. Forgive me. Thank you. Sorry, my mistake. Of course. Thank you. I would have gotten in trouble because I would have not gotten the x minus 2. I would have realized it in a minute, but I'm happy and glad that you did. It saves me going back. Thank you. So I have to use this. So what will be the next step that I have to write? Value of 4. Although that is 4, I have to show this first. Times less than epsilon. Now I can write that the absolute value of 4 is. Now I cheat a little bit. It's not cheating. I know what I have to get. So what should I do to both sides to get close to this? It's obvious. Divide by 4, right? Oh, very good. And now I compare, and I'm done. So please tell me, what is delta? What does delta equal to? What do you think?
Epsilon divided by 4.
Absolutely. And it's done.
So we can just say 1x.
x minus 2 delta.
I'm comparing. I'm not taking anything away. I started here, and I want to get here. And I did. I got the absolute value of x minus 2 on one side, simplifying algebraically. And this must be nothing else but delta. Okay, let's make up another one.
So for that question, that would be the answer. Delta.
That's it. There is a second part. There's a second part of, but all I want you to write is just this, and you don't have to do anything else. But I want you to understand that the precise definition has this double equivalence symbol, meaning this implies this, this implies this. So this was one way, and the second way, all I want you to write is show that delta equals epsilon over 4 works by reversing the steps in part 1. And this is part 1. This whole thing is part 1. Show that delta, which is epsilon over 4, works by reversing the steps in part 1. I'm done. I'm happy with that. Yes, please, Ian.
Part 2, that question, we be given an answer. We be given x minus 2.
You mean from here?
Yes.
No, from here we'll do this. I will write the absolute value of x minus 2 is less than epsilon over 2. Then I will multiply both sides by 4 to get this. Then I will put that 4 and absolute value of 4 are the same. Then I will state this property going backwards, which is this. Then I will distribute, which is this. And then I will have to separate negative 8 into 3 minus 11. And I will show that I went back to this. So I started here to get this, and then the reverse, I started here to get this.
Will we be asked part 2 without doing part 1?
No, you have to show part 1, and then you can, for part 2, I'm happy if you just remember to write this, which tells me that you know that you have to show the proof both ways. And I'm fine with just that sentence. You don't have to reverse anything.
I would just say that.
You just write that, and I'm good enough. So now I would like to choose one more, and then move on. So please choose another linear function. I'm happy. Yes?
Can we actually do B on the sheet?
Yes, of course. Let's do B. So we have limit as x approaches negative 2, good idea, over x squared minus 4 over 6x plus 12 equals negative 2/3. Perfect idea. Perfect. And then we look at the infinite limits, because there is a definition also for infinite limits, not just for limits that exist. There is a precise definition. So this is called, this has two names. This definition that we just wrote has two names. One name is the precise definition of the limit, and the second name is the Epsilon-Delta definition of the limit. One time I forgot to mention in class that the precise definition of the limit is the same with Epsilon-Delta, and on the test I wrote Epsilon-Delta, and only a couple of students understood that that's what I meant, so I'm going to have to write it down because I don't want to forget. So precise definition of the limit, or also known as Epsilon-Delta definition of the limit. Both names are used, either Epsilon-Delta or the precise. Okay, so we have this limit. First of all, please plug it in and tell me if this is correct. It's x squared minus 4. So it's 4 minus 4 is 0. It's from your book, and I think I copied it incorrectly. I just realized that. Because the top is 0 And the oh yeah, because we have to simplify. Yes, that's okay. Everything is good. So when you plug in -2, you get 0 over 0. So we have to simplify it. So the limit, x approaches -2. What do we need to do what do I know immediately that when I plug in -2 and I get 0, what do I know for both top and bottom? What do I know immediately? That there is a factor at the top of how much? Very good. And the factor at the bottom of, very good. So then the top is, let me write it again so for everyone to see, 6x plus 12. So this is limit, x approaches -2, and the top is x plus 2, x minus 2, and of course I have to have 6x plus 2. I'm allowed to simplify because x is never -2, so the new limit is x minus 2 over 6 when x approaches -2. And now I hope you agree then that the top is -4 and the bottom is 6, so the answer is indeed -2/3 from what we studied so far. So that is the limit. And if we want to, and we are asked to use the Epsilon-Delta definition, let's do it. Double equivalency. And please dictate. For every very good. There exists delta greater than 0. For every epsilon, I will find its corresponding delta such that yes, I pick x minus -2 now. Yes. Less than. Yes, every time I pick x close to -2, I will always find that the distance between, no, we simplified it. 6 minus the limit, the distance between this expression and the limit, plus 2/3 in absolute value, which is the distance. This is the distance. Distance between f of x and -2/3. This is how we write the distance between f of x and -2/3 must be less than. Excellent. Now I think we shed some light, and it's not as difficult as it seemed at first. Okay, where do I start? Where is the starting point? The distance between? Exactly, and -2/3. That's my starting point right here. Perfect. So x minus 2 over 6 plus 2/3 in absolute value less than epsilon. What do I do? Very good, excellent. Thank you. What now? Good. So then this one needs a 2. So now I'm ready. X minus 2. Good. Good. How much is that? Very good. Now I have to be careful what to do here. I'm not allowed to take anything out. I have to state a property. What is the property of the absolute value in which we have the absolute value of a ratio? Very similar to the absolute value of a product. Very similar to, very good, of course. So then what would I have to write here? Okay, now I can simplify one of them. Which one I simplify? And finally, what should I do to both sides? And let me show you where we're going. Because we know where we're going, but let me show you. This is where I'm going. So what am I doing to both sides? Good. So then I have the absolute value of x plus 2 less the 6 epsilon. Can anyone identify delta for us for any epsilon?
Delta equals 6 times
Very good. Very good. In step 2, what will I write in step 2? And this is done. The proof, formal proof, precise definition, epsilon-delta definition is done. What am I writing as the second part? Show
So that delta equals 6 epsilon works 5 versus
the steps in 1. Are we okay with this? Okay, let's look also at a infinite limit. There is also a definition of epsilon-delta definition, although it's not different. It's not that much different, but it has a different component here for infinite limits. So the limit of f of x as x approaches a is infinity if and only if for every large number n there is another number delta. Delta depends on n, such that every time I pick x close enough to a, which is this number, of course, f of x will be above n. We're going to talk only about positive infinity. This will be the same thing below n for negative infinity, but I'm happy with just positive infinity. Okay, so let's see how this works. So the double equivalency symbol for every n, which is a huge number now because we're talking about infinity, big number now, greater than 0, of course, there exists a delta greater than 0 such that every time I pick x close to a, not further away than delta, f of x, no absolute value, f of x will be above n. Let me give you an example of this situation, and then we'll apply it to a problem. Okay, so let's suppose I have this function. Let's say this is 10. Let's say this is n. And coming back, there exists an n greater than 0 such that for every n there exists a delta such that every time I pick x close to delta, so this point is 10 minus delta. This point is 10 plus delta. Every time I pick x close to 10, the distance is smaller than delta. Here's what happens. What will happen to f of x? So if this is my x, what will happen to f of x? Way above because the limit is infinity. So let's look at a numerical example and then a non-numerical example, like we did before. How close must we take x to 2 so that 3 divided by x minus 2 squared is greater than 100,000? So it is obvious that this is my function, and this is obvious, then this is my n. So I want to go back and try to find delta. Okay? How close must x be to 2? X and 2. How close must they be by finding delta? Finding delta will tell me how close I have to pick x to in this case, to 2. Okay, so let's copy that. I have 3 divided by x minus 2 squared greater than 100,000. At the end of the day, I want this. This is my target. How do I get that? What do I have to do first? Look at this inequality and say, oh, I know. Since this is always positive and it can never be 0 because x cannot be 2 as we discussed, I am allowed to do something that I normally say, no, don't do in an inequality. But since this is guaranteed to be positive and guaranteed not to be 0, what am I allowed to do now? Multiply both sides by it. Yes. So let's multiply by x minus 2 squared. So 3 greater than 100,000 times x minus 2 squared. Remember what I'm getting at. I want this, like always in these proofs. So how do I get closer to that? What should I do to both sides now? How? No, it's already factored. Everything is factored.
Check the square root.
Not yet. I'm not there yet. I have to get rid of this. Yes. So I have x minus 2 squared less than 3 divided by 100,000. Good. Now, this is another thing that I say, you cannot ever divide both sides of an inequality. Take the square root of both sides of an inequality, unless you know for sure that these are two positive numbers. For example, if you have 9 less than 16, is this true? I can take the square root. I can consider this. It's true. And the same thing here. This is always positive, and this is always positive. For that reason, and that reason alone, I'm allowed to take the square root. But when I take the square root from x minus 2 squared, what do I write? If I don't know x, what does the square root of x squared equal to? If I don't know x. Thank you. Exactly. Exactly. That's why when I take the square root from this, where's my thing? What do you think I'm going to get? Exactly. So, how much is delta? Anyone? So how close can I choose x to 2 that guarantees that f of x is greater than 100,000? This close. That's all. Yes?
Can you just explain real quick what happened to the minus 2?
Nothing. It's still here. I was asked to find delta.
Okay.
I didn't do anything to it. we're asked to find delta. How close should x be chosen to 2 so that it's guaranteed that the answer of the f of x is above 100,000? And we have to choose x not further away from 2 than this number. How much did we get? Roughly? 0.005? Okay, so I have to choose x. So x minus 2, I have to choose x on the left or on the right-hand side of 2, not further away than 2.005 or 2 minus 0.005. So if I choose, I have to choose between these two. This one is 2 minus 0.005, and this one is 2.005. If I choose here and go up, it's guaranteed that f of x will be over 100,000. Guaranteed. Okay, so let's finish this up with this non-numerical example. Any questions on this? Okay, so prove that the limit of 100 over x plus 4 to the 4th power equals infinity as x approaches -4. So, is this true? Yes. It's 100 divided by positive no matter what. If you want to show left or right, which we should, this will still be 0 from the left, 0 from the right. 100 over positive 0 is infinity, no matter what. So this is equivalent to saying that for every n greater than 0, I will find a delta greater than 0 such that nothing different other than the fact that we are using n. 0 less than x plus 4 less than delta will imply, can anyone tell us what we will imply? And this is done. It will imply that 100 over x plus 4 to the 4th power will be greater than yes, n. Very good. I know where to start. I know what I'm trying to get to. And let's continue. Where do I start? Exactly what I have, because I don't have anything here. This is n is given. It's not given per se, but it's the known number. So this is where my starting point is. What should I do to it? Exactly what I did 2 minutes ago. Very good. Good. I can, very good. Very good. Perfect. What do I have to do next? Exactly. I will take the 4th root from both sides. And careful what I write on the left. The right is very clear. But what do I write on the left? Very good. And I'm done. Can anyone give us delta? And it's done. Any questions? Any questions? Section 2.5, continuity. Say it again. Yes, I printed out everything for you. I think they were so sweet that I had to chew them up or something. I'm pretty sure I left them in the copy machine. I don't need them, but I really wanted you to have them, but I'll have them for you on Monday. Okay. Now, continuity is a different concept. So let's discuss what we know so far from this course. We know that we can determine the slope of a secant line. And if we manipulate that a little bit, we can determine the slope of the tangent line. We know what a limit is. We know that we have so many different types of limits in which the answer is infinity. They can be simplified. The function can be simplified, rationalized, and so on and so forth. Now we know that there is something called a precise definition, something that shows the mechanism behind a function whose limit is such and such. We know the difference quotient is a key concept in this course. So we know now how to find and simplify the difference quotient for many, many functions. Okay. Now the concept of continuity is a little bit different than a function having a limit at a point or not. So we know that, for example, for this function, I'm picking a number, and now I'm really have allegiance to 5 and 2, since I mentioned that so many times on that problem. I know you know that limit as x approaches 2 from either side from this function f of x, you know it is what? 5. Does the function have to exist at that point? No. As long as both sides approach the same number, the function doesn't have to be defined at that point. Now, for a function to be continuous, so for example, these are continuous functions. Polynomial functions are continuous. I would like you to tell me what function am I graphing now? Exponent, very good. Exponential function. Let's say 2 to the x. Continuous. What function am I graphing now? Natural log. Good. These are all continuous functions. As you noticed, I put my marker on paper, I graphed without lifting it off the paper, and I'm done. For example, this is not a continuous function. I had to graph this, I had to stop and put the open point, and I had to continue. So this is not a continuous function. Now this is now a continuous function. As you see, I graphed it without lifting my marker off the paper. So when is a function continuous at the point? Major definition. Continuity at a point. Major definition. So at this point, how would you describe that this function is continuous at that point?
I mean, F2
Exactly. Is the same and equals what?
is 5. Or the same as
Exactly. So the limit as x approaches 2 from the left of f of x equals, we should write a, but since I gave you this example, that's fine. Limit as x approaches 2 from the right from f of x must equal exactly. This is the definition of continuity at the point. In which situations is a function discontinuous? Discontinuous functions.
the left and right.
Here's an example. This is a jump. Jump discontinuity. Here's another situation. What type of discontinuity is this? It's clear. It's discontinuous at that point. It's called infinite discontinuity. And there is a third type. Very important. This is a so-called removable discontinuity. Obviously here, the limit from the left and the limit from the right and the function values are not the same. Here, the limit from the left, the limit from the right, they don't even exist. So it's clearly discontinuity. It has an infinite discontinuity. Here, what happens is the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, but it does not equal f of a. This is a removable discontinuity. Okay, why is it called removable? It's called removable because I can define this function slightly differently and fill this in. Here I cannot do that. Even if I try, there is nothing I can do to make this continuous. This one is the only one that I can make it continuous by redefining the function slightly. This one I can never make it continuous. This is the only one that I can make it continuous. That's why it's called removable discontinuity. It's the only one that I can work on and get a continuous function out of it. I still have time? Yes. 10 minutes. Okay. I would like to graph or start by looking at an example in which we want to make a function continuous by determining or finding a parameter. Okay. On page 129, of course, any combination of continuous functions would be continuous. So if two functions are continuous and I add them up, the new function is continuous. If two functions are continuous and I subtract them, the new function would be continuous. So any combo of continuous functions would be continuous. Okay, so let's look at problem 46, in which I'm given a piecewise defined function. It has three pieces. It has x squared minus 4 over x minus 2 for x less than 2. It has ax squared minus bx plus 3 for 2 and 3. Close at 2, open at 3. And 2x minus a plus b for x greater than or equal to 3. Here's the question. Find the values of a and b that make f continuous everywhere. Okay. I'll say, whoops, what is this? What am I trying to do here? Well, yes.
Is that ax squared minus b?
Ax squared minus bx plus 3, comma.
And what's that? That b as well?
You mean here?
No, the next one.
2x minus a plus b. Oh, sorry about that. Sorry, my handwriting. Okay. Yes, please.
I have an idea.
Please.
I think you can take the limit of as x approached to 2 on the first part. Yeah, and then from there, you try to define that with ax squared minus bx plus 3.
You're on the right track. Yes, you're on the right track. Okay, so first of all, I look at this function and I see something interesting here. And I know I sound like a broken record, and I always do. Simplify factor, simplify factor, simplify factor. Okay? So then I will definitely take this aside, and I know how to factor the top, which is very good. Since x is not 2, and I don't have to state any restrictions, I can do this. So the top one is x plus 2. Do you all agree?
Yes.
So now the simplified form of this function is really x plus 2 for x less than 2. It's ax squared minus bx plus 3 for this. And it's 2x minus a plus b for this. I didn't want to forget, there were a few problems that we did not do from the previous handout, and nobody said anything. Did you work on those problems? Did you have questions on those problems? Are you going to work on those problems this weekend, please? The ones that we did not do in class. Okay, perfect. Now, one theorem I would like to state, which I did. I mentioned it a few minutes ago, but I want to write it down. All polynomial functions are always. All polynomial functions are continuous. They are friendly functions. You can graph them without lifting the pencil or marker or pen off the paper. Good. So then I'm asking you, will x plus 2 be continuous on this interval? X plus 2 is a polynomial function. It's continuous everywhere. Will this be continuous on this interval? It's continuous on everything. Will it be continuous to the left of 2?
Yes.
Of course. Will this polynomial function, which is quadratic, be continuous between 2 and 3? Of course. Will this linear function be continuous to the right of 3?
Yeah.
I'm going to have to write this down. And here's how I write it. Yes, please. Tony?
Okay, I'll let you finish.
Okay. X plus 2 is a poly. Therefore, continuous on negative infinity to 2. Ax squared minus bx plus 3 is a poly. Therefore, continuous on open to 3. 2x minus a plus. I'm stating this theorem. I'm quoting this theorem every time I write this to make sure that I show that I understand that each and every portion itself is continuous.
Shouldn't that be a bracket?
Nope. Careful. Is a poly. Therefore, continuous on open 3 infinity. Now, what do I need to discuss? I discussed negative infinity to 2. I discussed 2 to 3. I discussed 3 to infinity. What do I have to discuss next? Continuity at x equals 2. After that, continuity at x equals 3. Good. Continuity at 2. What is the definition of continuity at the point? Please dictate. Limit as x approaches 2 from the left. Of what? Precisely of what? Very good. From the left. Very good. Must equal exactly what? Limit as x approaches 2 from the right. From what? From the right of 2. Very good. Very good. It must precisely equal, no question about that, what? Let's write it for everyone to see. It may be 4, I'm not sure. F of?
2.
Very good. Let's write the same definition for continuity at 3. Can anyone dictate? From precisely which branch? Very good. Must definitely equal. Limit. X approaches 3 from the right. From precisely what?
2x.
And must definitely equal. We didn't do anything yet. We did not calculate these limits yet. We just wrote the definition of continuity at the point for x equals 2 and the same thing for x equals 3. Good. Now please give me this answer. Exactly. Now please give me this answer. You have to give it in each piece. What is the first piece?
4a.
Good.
2x plus
2b, you're replacing x by 2 plus 3. Very good. And now I need this. And I have to go back to the function, and you'll tell me, where do I plug 2 in? Top branch, middle branch, or bottom branch? Middle branch, of course, because I have x equals 2 here. So it's still the same thing, right? 4a minus 2b plus 3. Leave it alone for a moment. Let's go to 3. I will not go over, promise. Good. So please give me this. 9a indeed.
Minus 9.
Very good. Excellent. Please give me this.
6.
Yes.
Minus 5.
You cannot do anything to a and b. You don't have them. So 6 minus a plus b. Good. Now I need this. Let's go back to the function and decide which branch I plug it in. Bottom indeed. So it's 6. It's the same thing. 6 minus a plus b. 6 minus a plus b. How many variables does the problem have? How many equations I need? Do you have 2 equations for me that I could create a system with so I can determine those? Dictate, please, to me 2 equations. I want to write 2 equations, different equations, of course, that I will put together so I can solve for a and b. I'm ready.
4 equals 4a minus 2b plus 8.
Excellent. Is it clear? Once I get a and b and I put them back in the function, would you say that it's guaranteed that this function is continuous everywhere? Once I have a and b and I put them back in the function and I replace a and b with those numbers, is it guaranteed that f of x is continuous everywhere? We made it so. We stated these restrictions so that the limit from the left and from the right of 2 equal the function value of 2. That's how we came up with this. And the same thing at 3. The limit from the left, the limit from the right, and the function value at 3, they must be the same, because that's how we came up with that. So I have 1 more minute. I'm just going to clean it up, and I would like you to finish it up. Finish this, solving the system, okay? So I have 4a minus 2b, and then I will subtract 3 equals 1. And that's cleaned up here. And now here, this one, I will add a. So I have 10a. I will subtract b from both sides, minus 4b, and I will subtract 3. So I would like you to solve this system. You have several ways. You can eliminate by multiplying by -2, and so on and so forth.